In many respects, our moon is one of the strangest bodies in the entire solar system. Of all the terrestrial or four innermost planets, only Earth has such a large moon. Compared with the terrestrial planets, the moon's density is much lower than we might have expected. Compared with Earth, the chemistry is much different. Before the Apollo program, three major theories arose to dominate scientists' thinking about how the moon was formed. One suggests that the moon split off from the Earth and was flung into orbit around our planet. A second theory suggests that the moon originated as a twin planet, perhaps from materials left over from the formation of the Earth. The third theory holds that the moon was captured by the Earth's gravitational attraction, having been formed somewhere else in the solar system. There are problems with each theory. It has been suggested that it would be easier to explain our moon's absence than its presence. Nevertheless, from the data returned by the remarkable Apollo flights, as well as unmanned missions, we have learned a great deal about the moon's evolution and early history. It has become, in a sense, an emerging planet. Unless it split off from another planet, it must have originated as a tiny body, perhaps one something like Phobos, one of the moons of the planet Mars. And it grew by a process of accretion, an accumulation of objects drawn together, often in massive collisions by gravitational attraction. These objects ranged from microscopic dust particles to asteroids. By 4.6 billion years ago, the moon had reached its present dimensions. During the last 10 to 100,000 years of this primeval bombardment, the collisions may have generated so much heat that the entire outer shell of the moon may have turned into a seething global ocean of molten silicate materials. Once bombardment slowed, the liquid shell began to cool, solidifying over a period of tens of millions of years. Crystals rich in calcium and aluminum formed. They rose to the surface and produced a mush which eventually solidified to become the dominant light-colored material we call the highlands. Simultaneously, dense crystals rich in magnesium and iron formed and sank to the bottom, becoming a distinct dense layer. There was now a lunar crust, a product of millions of years of crystallization. 100 to 300 million years later, radioactive heating became extensive enough to melt materials in the shell just beneath the crust. The melting produced pockets of liquid, giving rise to volcanic eruptions 4.4 to 4.3 billion years ago. At the same time, it seems that globules of molten material rich in metallic iron may have accumulated, and they settled down into the center to form a core. If 2 to 3% of the original moon consisted of metallic iron, the core could have a radius about 1/5 that of the whole globe. Such a differentiated moon, with a crust, a mantle, and a core, came as quite a surprise to many scientists who had expected the moon to be homogeneous, with materials distributed more or less evenly throughout. A molten core rich in iron could have functioned as a huge dynamo, much like the Earth's core, and produced a magnetic field. This would explain the magnetic properties of many of the lunar rocks which have been returned by Apollo crews. According to theoretical studies, the moon and Earth serve as very efficient celestial vacuum cleaners. And within less than 100 million years after their formation, they should have swept up most objects in their vicinity. Surprisingly, 600 million years after the formation, or 1/2 billion years later than we would have expected, huge objects were still impacting on the moon, helping produce the rugged surface. Some of them were as large as the state of Rhode Island. The final ones blasted out the great circular basins we see on the moon's face today. One of the final large impacts, which we call the Imbrium event, produced the circular feature which now serves as the right eye of the man in the moon. By the time of the Imbrium impact, the exterior of the moon had cooled to depths well below the crust. The interior, by contrast, began to warm up, a result of natural radioactivity. At a depth of 150 miles, perhaps 300 miles, a zone began to melt, producing liquid silicate material that accumulated in pockets. The liquids then found their way to the surface, sometimes following fractures in the crust, sometimes forcing a passage through solid layers. One volcanic flow after another filled in the great basins produced by the large meteoroid impacts and became what Galileo Galilei called the lunar maria, or seas. After some 1.5 billion years, major volcanic activity on the moon had come to an end. Except for a last gasp of volcanic activity originating deep in the lunar interior, rare meteoroid impacts, such as the one which produced the crater Copernicus, and occasional small moonquakes. The peace of the moon has been largely undisturbed for 3,000 million years. Since the first manned Apollo landing in 1969, we have thus learned a great deal about those early events and processes which produced the moon. And it seems likely that similar events and processes were at work on our own planet. The Earth's early geologic records, however, have been largely obscured. For while at least 97% of the moon's rocks are older than 3 billion years, some 97% of the Earth's rocks are younger than 3 billion years. Almost all the older rocks have been destroyed by extensive volcanic activity, faulting, folding, erosion, sedimentation, and other geologic processes. What few of the ancient records we do still have on Earth are being illuminated by our lunar studies. For instance, rocks similar to those of the lunar highlands are found on Earth and may have been formed by a similar process. Counterparts to the Maria formations on the moon may be represented by certain very old volcanic formations on Earth. On a simple graph, the differences in global activity on the moon and Earth can be summarized with the level of activity plotted against time from 4.6 billion years ago to the present. It is clear that the moon had a violent and dynamic early history, and that major geologic activity had come to an end by 3 billion years ago, leaving the planet as virtually a dead body. It seems likely, though not yet certain, that the Earth experienced a very similar early history. But unlike the moon, the Earth did not die. Indeed, its geologic activity increased. By 500 million years ago, hard-shelled animals had appeared on Earth, and they left their fossils in rocks we find today. It was only about 200 million years ago that the present continent split and began to drift apart. a process which continues to this day. In essence, it is possible that the Earth and Moon had quite similar early histories, which should lead to a better insight into the first billion years of Earth's history than ever before. It is clear that the two bodies had widely divergent later histories. As scientists from a wide range of disciplines have come together to study the data returned from Apollo missions, there has been a rich interchange of ideas and knowledge and investigatory techniques. This has led to a clearer understanding of our solar system. The study of lunar rocks, for instance, has told us that the bulk chemistry of the Moon is quite different from that of the Earth, or meteorites, or the Sun. Our picture of the solar system is now quite unlike the one prior to Apollo. No longer would we expect the bulk chemistries of the inner planets and moons of the solar system to all be similar, for it is now clear that there are important differences. While the bodies have certain elements in common, those elements are combined in widely differing proportions. Compared with Earth, for example, the Moon is rich in calcium and aluminum and poor in sodium and water. In fact, the chemical dissimilarities are so great that the possibility that the Moon was derived from the Earth has essentially been eliminated, and the question of the Moon's origin is still unanswered. Apparently, the Moon and every other planet in our solar system have each a unique character, a unique story to tell. As we conclude Apollo with a manned flight to a region just east of the Sea of Serenity, we have opened a new chapter in science. In studying the Moon, we are taking our first close-up look through what has been called a window to the history of our solar system.